All right, so today we're going to look at graphs of polar equations, and these would be graphs that work only on a polar graph. They don't convert nicely over to a rectangular graph. And there's actually some kind of cool graphs. I ended the 6.3 lesson with kind of giving you some points. We basically made this big old XY table. Okay, not really XY, it's really an R theta table. An R theta table, and we plotted points, plotted points, plotted points, plotted points until we could get the gist of what these graphs look like. Now we're going to talk about two types of these polar graphs, and you don't get the benefit of watching this plot, so you just got to trust me. Here's what it looked like when we started plotting points. All right, this first example that we did is in this format right here. And we actually consider that it looks like this. It's R equals A cosine B theta. So the A and the B are those two numbers, and those numbers dictate kind of what this graph ends up doing. All right, now we're kind of trying to, ultimately, we're going to kind of cut to the chase on some of this. It probably won't stick as well in your brain as if you were in class, but here we go. Here's what the graph looked like when we graphed it. And we found that it kind of had, well, what it was called was a rose curve. And it started here. And I'm going to kind of, I can't really graph it as well as if we had plotted points, but ultimately I'm going to catch some key points here and see if I can't get it to sort of look like I want it to. And there. Okay, I'm going to go with this. Okay, so here's what it is. We started plotting points, and they started doing this business right here to us. It came around, and then it hit here, and then it came back up there, and then it kind of went through that pole and back up to there and back down here, and then it started back at the beginning. Right. It's called a rose curve. It's not very fancy, but it's like this little flower. Okay, so let's talk about just the parts of this and how we analyze a rose curve. The maximum R value is the farthest out you ever get from the pole. And you can see in the graph, the farthest out you get is 5. Okay, and it occurs, I guess, when a point on the curve is at the maximum. Now, again, you didn't see all the ordered pairs, but sometimes you might have gotten to this maximum through a negative R value. Like, for instance, the angle might have been this angle, but when we plugged it into the equation here, it ended up giving us a negative R value that shot us through up to there. So that's why we always look at the absolute value of R. It might have been a positive 5, might have been a negative 5, but I can just tell the farthest out it ever got was 5 units. Okay, the domain and range. The domain are your possible theta values. Well, I kind of dictated what theta values we were going to use, but you can always plug in whatever you want for theta. Now, the R values were dependent on that, and it was not just anything. We had to sit there and track our table and look, and the smallest R we ever got was a negative 5, and the largest R, and that was with a bracket, and the largest R we ever got was 5. Okay, the next thing was the symmetry. We have 3 types of symmetry. We're used to x-axis, y-axis, origin symmetry, but we don't have those parts on a polar graph, so we have to rename that. Instead of x-axis, we call it polar axis. Remember that the polar axis is the positive x-axis. It's just this piece right here. Instead of a y-axis, we call it a Pyrrha 2 axis. And instead of origin, it's called the pole. And so origin, remember, you can rotate it 180 degrees and it lands on top of itself. So looking at this particular graph, you're looking at if it folded over or flipped over this axis, it's going to flip and land on top of itself. But that will not be the case on the pi/2 line. These two petals do not flip over and land on top of the other side properly. Also, if I rotate it 180 degrees, this petal, and we do call these petals, it's a rose petal. And so if I rotated that 180 degrees, it is not landing on top of itself. So this has polar axis symmetry. Now our goal then is to look at that and decide, okay, as I start changing this 5 and I start changing this 3, what happens to the graph and what happens to all this info over here? Okay, so after playing around in Desmos for quite a while and looking at, as we change that A and that B, and again, remember your format here is R equals A cosine, could be sine, B theta. We changed the A, we changed the B, we changed from sine to cosine and back and forth, looking for patterns of what happens. Here's what we discovered. That the size of the petals are always going to be whatever your A value is. That tells you how far out from the pole to draw the petals. That's your max R value. Okay, how many petals there are is dictated by the B value. And if B is odd, it's different than if B is even. If B is odd, then there are B petals. So if you, well, let me finish writing. If B is even, then there are 2 B petals. So for instance, if this was a 3, like it was on that previous example, we had 3 petals. But if that happened to be a 4, since that would be an even number, you'd have twice that many petals. You'd end up with 8 petals. So there's a big difference. If this is even, you can start getting a lot of petals going on there. Okay, now, where do we put the petals? All right, we determined that was dictated by, well, a few things. It was dictated by cosine versus sine, but also that B value played a part. Cosine is the easiest scenario. Now, one thing to note is that however many petals there are, they're always evenly distributed around your graph. So if there are 4 petals, you would take 360 divided by 4, that's 90. So you'd have one every 90 degrees. They don't all come out that nice. If there's 5 petals, 360 divided by 5 is 72 degrees. That's not as pretty, but we made it work. So cosine, again, is your easier option. What we learned on cosine is we always started with a petal over here on the polar axis. So your first petal would always land there. And then we would have to decide where to put the other petals so that they evenly distributed around there. But your first petal is always on the polar axis if it's a cosine. If it's a sine, that was not the case. Different things happened with sine. If the B value was odd versus even, okay, if it was odd, instead of the first petal being on the polar axis, the first petal is on the pi/2 line. But it's not that easy. The pi/2 line, or I guess I've been calling it a pi/2 axis. Really, the pi/2 axis is the full axis, but the polar axis is really just considered this, the right side of that polar axis, because you're kind of going around. But when your first petal's on the pi/2 axis, sometimes it's up here and sometimes it's down here. And what we determined, let me put a period there, it alternates starting up versus starting down. And getting to be a lot here. Did you write little? Sorry. So here we've got this. If your B value is a 1, then your first petal is up. If your B value is 3, because remember we're doing odds, then your first petal is down. If you have a B value of 5, it's up. 7, the first petal's down. 8, it's up. Or I'm sorry, 9. Okay, so I'm not going to get 9, probably I'm not going to get that crazy, but it alternates up, down, up, down, up, down. So it starts with an up. If B is 1, then it starts up, and then you evenly distribute from there. If B is 3, your first one is down, and then you evenly distribute from that direction. So alternates up and down. If it's even, okay, then the petals and there's different words we use for this. I usually let the students kind of pick a word that makes sense to them. The petals are not on the axes. So we say they avoid the axes, they dodge the axes, they hit the gaps, whatever the case may be. So for instance, if you have a graph here, and let's pretend that the B value was a 2. If B was 2, that means it's even. Now remember, if this is a 2, there's twice that many petals. So a 2 here means I'd have 4 petals. And these petals are specifically not on the axes, and they're going to get evenly distributed. So you're going to end up with your petals like in the gaps, in the 45s. It would look like that. Something to this effect. That's what I mean by they're not on the axes. They will never land. Now, what if you had 8 petals? Well, then you would have to sneak 2 petals inside here. Now, it would not look like what I'm doing right here. You'd actually, I don't even want to do that. It's going to look terrible. I'm going to undo, undo, undo. It would look more like this. You'd have to evenly distribute them. So this is sort of the pattern that we use to draw. It kind of swoops around, and then boom, and boom, like this. Something to that effect. There's your 8 petals. The trick on this is that they have to be evenly dispersed. And so you got to make sure that the distance between this one and this one is the same as this one to this one. So sometimes what happens is we make these kind of close and these are kind of close, and then there's like this big gap between these. Try to make them all evenly dispersed. They are not going to necessarily land on grid lines nicely. Like this one, the 8, it doesn't. It doesn't land. So try to just kind of space them evenly. All right, I'm going to let it go at that. Let's keep moving. Next thing we have is the symmetry. All right, if you have symmetry with an even number of petals, so it doesn't matter if it's cosine or sine, if you have an even number of petals, you're going to have all 3 types of symmetry. So we would say they have polar axis symmetry, and we would write them. We don't get to say all 3. You have to know what they are. Pi over 2 axis symmetry and pole symmetry. It's this beautiful symmetrical rose curve. However, if you have an odd number of petals, that will not be the case. Cosine will only have polar axis. That would have been like the example we had. And this should kind of make sense because cosine is kind of like your x, so it's going to have like x-axis symmetry. Sine is like your y, so it's going to have pi over 2 axis symmetry. On your rose curves, your domain, always going to be negative infinity to infinity. And your range, you might want to look back at the one we did. The range is always coming back. The range is your R value. I maybe didn't specify that, but domain is your possible thetas. Your range is your possible R values. And your R, remember your max R value is how big the petal gets. And so that comes from anywhere getting a negative R value to a positive R value, okay? And it's not really R's. Remember that the R came from this leading coefficient here. So really what I should be writing there is negative A to positive A. That's what your range will be on these rose curves. Now, I have several worksheets. We're going to practice this a bunch, but let's go ahead and do these 4 rose curves, and I'll kind of walk you through all those things you have to think about. So let's start with this first one. This tells me how big to make the petal. So I know they're going to go to the 4th ring here. The 3 is odd. That means I have 3 petals. It's a sign. So this is the version where it alternates up, down, up, down, up, down. And remember, 1 is an up, so 3 is a down. So I know that my first petal is going to be down, and it's going to be on that 4th ring. Your radius is 4 there. And if I take 360 and divide it by 3, that's 120. So I know that I'm going to have another petal, 120 this direction, and 120 this direction, and then this is going to naturally be another 120. So I would have a petal here, and you take a glance, make sure they look evenly distributed, and then you sort of draw this through. Did you ever have a spirograph as a kid? That thing that you would have those little round discs and you would just draw these cool designs? Okay, it's kind of like that. All right, next one. On this one here, the 3 tells me that that's going to be my maximum radius, so I'm going to go 3 rings out when I'm drawing this. The 5 tells me how many petals. It's odd, so I'm going to have exactly that many petals. I'm going to have 5 petals. But this one is a cosine. And remember that cosine always, always, always has a petal on the right, on that polar axis. So there's my first one. Now, 360 divided by 5 is actually 72. So these are going to not land on the on the grid line for your unit circle. So I'm just going to kind of estimate. I know that this is 60. That's my 75 line right there. So 72 degrees that way is about right there. And then I'm going to go 72 degrees down also. So that's about right there. And now I've got 2 more petals to get. And a 72 and a 72 is a 144. So 144 would be, I don't know, somewhere like right there-ish. And let's go ahead and put a matching point. Remember all the symmetry that this is going to have. Somewhere like right there. And take a glance, and hopefully they look sort of evenly dispersed. And then you start drawing your petals in there. Kind of did that in a weird order, sorry. There it is. Okay, let's try again. This one has an even finally. Okay, so we're going to have an even number of petals. We're going to be 5 rings out, so it's going to be a big one here. Remember that if this is even, then you double the number of petals. So this is going to have 8 petals. Oh, this is going to be like that one I drew earlier because it's a sine. And remember, sine purposely does not hit any of your axes. So I have to evenly distribute 8 petals throughout all this. All right, so again, you don't want to sit there and put it like right here and here, because then your next one would be here, and you can see those are not evenly dispersed. So you kind of have to, like on this, typically they don't hit perfectly on the axes. I don't get super caught up on exactly where they're going to fall, but I kind of want it to look evenly dispersed when you do it. So try to think of that symmetry that you're going to have on the even number of petals. This point should reflect over to this point. And equally, this point should reflect down to that point. So try to keep that symmetry going. And then hopefully they look sort of evenly dispersed. And then you start drawing these loops. Okay, so usually they just draw through and then you kind of skip over some. Looks something like this. Now, they're all going to go through the pole and they do not overlap. So be careful that your petals don't overlap. All right, last one. Let's see. I'm going to give you a minute. I'm not going to give it away. Can you envision what all of this is going to do? What are we going to be looking at? What's the 3 do? What's the 2 mean? And since it's a cosine, where's it going to start? All right, let's see if you agree with what I say. I think you're going to be 3 rings out. That's your radius, 3. The 2 means you're going to have twice, that's even, so twice that many petals. I'm going to have 4 petals. And because it's cosine, your first one lands on the polar axis right here. 4 petals evenly dispersed. That's going to land beautifully right here on all of your axes. And there we go. Okay, that's the rose curve. You might want to practice that on your worksheet before we jump into the next one. This is a totally different polar graph. This one is graphed. Well, let's start with the equation. The equation looks like this. R equals A. This can be a plus. It can also be a minus. It doesn't mean plus or minus, but it can be either plus or minus. And then you're going to have another number here. And then this is a sine theta. It could also be a cosine theta. And then what we did again is we made this big table of values. We graphed it, watched it graph, so you kind of knew how to draw these. And this gave us a limachon. I don't know if I'm pronouncing. I always feel like I pronounce that incorrectly, but it's a limachon. It's a French word, and it has a little accent mark on it. It's underneath that C. I just usually do it like a little, oops, do a little squiggle underneath the C there. Something like that. Okay, limachon. All right, so now here's what we found with this particular graph. Here's what it looked like when we graphed it. I'm going to plot some key points so that I can draw this accurately. It looked something like this. All right, so here's how it graphed. It started and made kind of like this little loop, and it swooped around and caught right there, made a big loop. Nice, round, bubbly looking thing like that. That's what it looked like. That's called our limachon. Now, our maximum R value on this particular graph, we were just looking at what's the farthest out it ever gets, and that would be a radius of 4. So our max R value was a 4. The domain and range in this one was a negative infinity to infinity. And when we traced this and we watched the R value from our table, we ended up with it. The smallest was a -2 and the biggest was a 4. And then when we looked at this graph, we thought, okay, the symmetry appears to have pi/2 axis symmetry. And that was the only symmetry it had. Okay, so now what we did is we went into Desmos and we played around and we changed the A, we changed the B, we changed a plus to a minus, sine, cosine, changed all the stuff up looking for patterns. And now let's go ahead and talk about what we came up with. I think the first thing that we pretty quickly realized is, where does this loop go? And it varied. Sometimes it went up, sometimes it went down, sometimes it was to the right, sometimes it was to the left. But it was pretty straightforward of where it would go. So I'm just going to do a quick little axes here. I don't know if that's the easiest way or not. But if you had a positive with a cosine, then the big loop, and I'm just going to draw it over here as like a big circle, but it was always over there to the right. Versus if it was a cosine with a minus, then it was over here on the left side of it. If we had sine, then the big loop was up and down. And if it was a plus, it was up. And if it was a minus, then it was down. So ideally, that made pretty good sense to us. Cosines are like x's for us. So it makes sense it was on the left and right. Pluses are on the right, minuses are on the left. Same deal with the sine, only you're going up and down. So figuring out where they went, that went pretty fast. As far as the symmetry is concerned, these definitely only have one type of symmetry, and it's going to depend on whether it's a cosine or a sine. The cosines always had polar axis symmetry. And sines always had pi over 2 axis symmetry. The graph, okay, this is not the ideal time to talk about it, but it's where I had space to write it. So the graph is always going to kind of swoop right through the pole as you're drawing it, but it also is going to have it's not really x-intercepts. They're going to have extra intercepts, I should say. So let me draw this a little bit better. Let's say we were doing this one right here. I'm going to draw it a little bit bigger. And if we were doing that loop thing, so it would look something like this. It would have this little loop here, and it would come through the pole, and it would swoop up past and come back around and back to there, something like this. Well, these intercepts right here, where it crossed that axis, always matched whatever value that was. So it crosses the axes at A. Now that's like on the sides of the big loop, not the big loop itself. Okay, so the fun part was kind of figuring out how big these loops are and how that's decided. All right, so again, remembering what this equation, I need to kind of write this in here better, but remember the equation is R equals A, and it could be a plus, it could be a minus, and then you have a B, either a sine or a cosine theta. The big loop, how big to make the big loop, was always A plus B. Now, when I talk about A and B, I am 100% ignoring what this sign is here. The plus or minus is dictating which direction it goes. So when I say A plus B, if this happens to be a minus, I'm not thinking that as a negative B. I'm just looking at these two numbers, A plus B. And to get your little loop, you would always do B minus A. Okay, so as far as domain and range, again, not the ideal place to put it, but I had room to write it, so I'm going to do it. Negative infinity to infinity was domain, always going to be. Range, I'm going to go ahead and tell you what this range is. If you peek back at the previous one where we did domain and range, and I just told you what we found, it really has to do with where your big loop and your little loop are. So again, I'm going to draw this. I'm going to draw it a different way than you've seen, just so you get used to this idea of I might have this little loop, and then I'm going to have this big loop. It's going to cross here and here. I'm just making this up. These are kind of the 4 key points we draw. And so here's my little loop, and then here's my big loop. And there's my loop. Oops, that should have swooped into the pole right there. Sorry. Okay. So what we found is that the biggest R value always came from wherever the biggest part of the loop was. And so whatever that was the bigger end of your range. And remember that comes from this right here. So this was always A plus B. And then the smallest R value always came from the little loop. But the little loop actually is coming from negative R values. So when we were looking at our table, everything that made the little loop had a negative R value. So this little loop, whatever that distance is, which is this right here, that little loop, but it was always the negative version of that. So it was always an A minus B. So that right there is your range. That'll make more sense later on, I think. But we discovered that not all limacons have that little loop. And it has to do with the value. Oh, look at this. That's wrong. Why is that there? I wonder if I caught that in class. This is supposed to be an R equals A plus or minus B. We can go cosine. It doesn't matter. Cosine theta, something like this. That's a rose curve. We don't want that. Okay. So what we discovered, though, is that as this relationship between A and B changed, the little loop started to change in here. So if we want to have the little loop, then your A value has to be smaller than your B value. So looking at these two values here, if A is smaller than B, then you're going to have this little loop in here. But as A grew and A and B became the same, if A was equal to B, that little loop disappeared and it just came to a point right there, which should sort of make sense because remember, to get the little loop, you had to subtract the A and the B. And if they were equal, you'd subtract them and you'd get a 0. So that's why your little loop is 0 right there. But it got more extreme. As A got bigger than B, we even lost the well, not the indentation, but the point that it went to. And now it sort of just dented in. Now notice these new names that are coming in here. This is our normal one, our limacon with a loop. If you lose the loop entirely, if you turn your head sideways, that actually is a little heart shape. So it's called a cardioid, a cardioid. It's a heart, okay? Now this one, as your A gets bigger, you lose the point and it just becomes a little dimple. And we call it a dimpled limacon. And then as A gets really big, like twice of what B is, you even lose the dimple and it just becomes convex, which means it doesn't dent in at all. It sort of has this flat look to it. So this is the progression of what's going to happen, and you need to know that progression. All right, so here's the end. We're going to practice graphing all of these. So starting with this first one, it's a plus with a cosine. So I know it's going to be off to the right. I add the A and the B to get the maximum, and the maximum is going to be a 5. So I'm going to put a dot right here. That's my big loop. Notice that the A is smaller than the B, so I'm going to have a little loop, and the little loop is going to be 1. So I'm going to, you get that from subtracting those. So I'm going to have my little loop landing there. And then remember the other 2 points are your other intercepts along the other axis, and they're always equal to the A value. So that's going to land right here and right here. Those are your 2's. Okay, let's see if we can draw this. You start at the pole and you make your little loop. And then you swoop up past the axis, come catch that x-intercept, and keep going wide. Keep going wide. Oh, this is not going to be pretty. All right, and you hit right there. And you keep going wide, and then you swoop back up, and you hit right there. It's so tempting to do this right here. I'm going to draw it, and then I'm going to erase it. But you do this little loop, and then you kind of like, as soon as you hit that, you'd like, boom, you go down here. And this is not a nice bubbly shape. It's a real skinny, pointy thing. That is not the way limacons look. So try to make it nice and round. Okie doke. Next one. All right, let's see what we've got here. Looks like our A value is smaller than our B, so we're going to have a little loop again. It's a cosine, so it's going to open on the sides, except that it's a negative, so instead of opening over here on the right side, it's going to be over here on the left side now. All right, my big loop is going to be 4, and my little loop is going to be 2. That's the difference of your A and your B. And then it's going to cross the other axis at 1. All right, so those are the 4 points that you plot. You start at the pole, and you make your little loop like this. And then you swoop up past the axis, hit that, keep going wide, keep going wide, keep going wide. Catch that, keep going wide, come up, and hit this other dot, and back to the pole. All right, let's look at the next one. It's another cosine. Positive, so it's going to be on the right, but look at your A and your B. They're the same. All right, so it is going to be off to the right here, but this is your cardioid situation. You are not going to have this little loop. All you're going to have is the point where it hits right here in the middle. So it's going to have the point right here. You look at your A value for your other intercepts. 2 plus 2 is 4, so the big loop is going to go to 4. And here's what it looks like. Like that. Okie doke. Last one. Take a peek at it. See if you can think through it in your head before I give it all away. All right. It's a sign, finally. It's a plus, so we're going to be going upward. The big loop is going to be a 5. But in this case, notice that the A value is bigger than the B value. So this time, you're not going to have a loop. In fact, you're not going to have a point. You're not even going to have a dimple because the A is so much bigger. This is an example of a convex. It's just going to sort of get flat on the side. Now, the 4 is still going to be where it hits the other axes. So this is going to look kind of weird compared to the other one. And then as far as, no, there's not a little loop. But instead of this, when you find the difference and you're getting a 3, really what you're getting here is a 3 that's going to be this way, not like a 3 where it's an inner loop, not like that kind of a thing. Instead, it's a 3 the other direction, and it's where it goes flat on you. Let's see if I can draw this thing. All right, I'm going to start here, come around, get big there, come back here, come around, and then try to sort of make it obvious that it sort of went flat on us right there. Something to that effect. That's not awesome, but all right, that's it. There's your Limousin curves. So we've got rose curves, we've got Limousin curves. A lot of stuff to keep track of, but I've got lots of practice graphs for us also. All right, good luck.